Hi, welcome back. Today we're going to talk about how to interpret what a partial derivative is. So let's first again go back to our functions of one variable and talk about how we understand what that means. So often when we're talking about a function of one variable, we've got our graph of our function, and we're asking to take a derivative at a point. So think back to what that means to you. Um, there's normally two things that come to mind when you think about that. The first of which is maybe the slope of the tangent line. So we draw a line here, and the slope of this tangent line is what the derivative of the the function f of x is at that point. An alternative way that tangent line, that slope of the tangent line also means, is maybe the more physical, the more applied idea behind a derivative, which is what is the rate of change of the function as x varies. So we change x, and we see how does this function change uh, as we increase the x value. So in this example, maybe this is the number of widgets being produced, then what this slope here is saying the rate of change of the net number of widgets being produced is decreasing at this point. We can calculate how much that is. All right, so now let's take this and go to higher dimensions. So now what we have, instead of talking a graph that's this curve, now our graph looks like a surface. So what does it mean for us to take the partial derivative with respect to x of f of xy? So again, we're taking this partial derivative over here at x equals a. Now we're taking the partial derivative at a point a, b. Right? So a is some number, b is some number. So when we draw this graph and we say, I want to know what the partial derivative is with respect to x, then remember, that's what happens when we fix b. Right? So in this direction, this is x. This direction, this is y. And so we're going to fix the value for y. And we want to know, as x changes, what is the slope of that tangent line, the tangent line to the curve there on this surface, when y is equal to b. But at this point, when x is equal to a. So we're walking along this line here, where y is equal to b, and we get to this point a, and we say, well, what's the tangent line here? So we can understand this as a tangent line, but if we want to talk about it in terms of rate of change, then what we're asking is, if y is fixed, what is the rate of change of f of xy as x changes? So when we're talking about these partial derivatives, what we're talking about is we're saying, let's fix a value of y and see how x is changing at that spot. So I created a visualization for us to help us understand this a little bit better. So here is the graph of an equation. Now, it's a crazy equation, but I made it a crazy equation so that we could have something that had a bunch of bumps and curves, all located around x and y are both 0. All right, so we've got our x variable. If we're This is normally the orientation that we look at our graph, where x is coming out towards us, y is sloping off here to the right, and z is going upwards. Now, what I've done here is I've considered what would happen if I moved this point AB and moved it around. And what we want to do is we want to find the slope of, we want to find the partial derivative at a point AB that's moving around this surface. Okay, so what's going to be very helpful, I'm going to turn this graph a little bit this way. So now x is coming out towards us, but a little bit to the right instead of a little bit to the left, as we normally used to drawing it. And now I'm going to do some slicing. So if I'm setting y equal to b, so if I'm here at this point, what does y equal b look like? It looks like a plane that slices through our surface in this way. Right? So from the side, this is what happens when we slice our surface at this plane y equals b. For different values of b, we get a different slice. Right over here, look at this interesting slice. Definitely goes down and then up. And over here, it's almost like it goes up and then down. As you choose different values of b, you get different ways that the surface looks like. So these are fixed b's, and this is what the slice of the plane looks like. And now what we want is we want to know what is, if we're trying to figure out what is the partial derivative of f of xy at a comma b, well, what we're doing is we're now moving x. We're moving x along this fixed curve. It's fixed because b is fixed. But now we're asking, what's the slope of the tangent line at, let's add these things, at 1.5 comma 0.11? Well, we find the slope of the tangent line of this red curve. This red curve is where b is fixed to be 0.11, and then we say, well, as we move up here, this slope of this tangent line is, half, something less than 1, but positive. All right, so let's go back to our picture, and let's instead of looking at the partial derivative with respect to y, let's take the part, no, that was the part, sorry. Instead of taking the partial derivative with respect to x, we now take the partial derivative with respect to y. And when we do that, we're fixing x to be equal to a value. So here we'll fix x to be equal to a. And for different values of a, this curve looks different. This slice that is the slice of what happens when you take your function, where you set x to be equal to a, you get different shapes of that function. But for some fixed a, for example, a is equal to 0, when a is equal to 0, then what we're doing is we're looking how does y change as what's the slope of this tangent line of the blue curve. The blue curve represents x is equal to 0, and what we're doing is we're looking for the slope of the tangent line here. So at 0, comma, -1, then what we can see here is that what is the slope of this tangent line? It's negative 1/2 or so. And what that's saying is that the partial derivative with respect to y of f of xy at the point 0, comma, -1 is about -1/2. All right, so I hope, so you'll play around with this on your own. You'll see what happens. We can see the different slices, the different ways of what it looks like to have f of x and f of fixing x is equal to a or y is equal to b. And then when you just look in one direction, you can really see this partial derivative in terms of a rate of change of one function where the other variables are kept constant. All right, I will see you shortly.